Hi, I'm Jessica, and welcome to today's crash course on finding the perimeter and area of plane figures. So in today's crash course, we're going to be looking at the perimeter and area of triangles, quadrilaterals, regular polygons, decomposable figures, and circles. We're also going to take a look at arc length of a circle and the area of a circular sector. So let's go. The biggest trick to these problems is really trying to figure out, are we dealing with perimeter or area in a given problem? So we're going to take a look at some of the words that can be giveaways for us to help us figure out whether or not we're dealing in perimeter or area. Because it's not always clear. Sometimes they'll tell us blatantly in the problem, and other times they're going to use synonyms for it, each of them. So I've got a little table here that summarizes some of the synonyms that are often used for perimeter and those for area. So for perimeter, it's often words like contour or border. Examples of perimeter problems include installing a fence, installing moldings, measuring a frame, and of course our units are always in centimeters, decimeters, meters, or something of the like. For area, words like surface or coverage are often used. And examples would be painting a fence, covering a floor, mowing the lawn. Of course, the units in area are always in units squared. So we've got centimeter squared, decimeter squared, meter squared, etc. Let's go. Okay, so before we start any calculations on our first example here, we've got to determine whether or not we're dealing with an area problem or a perimeter problem, because we don't want to be calculating for nothing or getting ourselves down the wrong path. So let's just take a quick read through here. The top of a removable board on a child's toy is to be varnished. What is the amount of surface to be varnished? Before we go any further, we got to answer that question. What type of problem is this? Is this an area problem or is this a perimeter problem? If you guessed area, you are correct. So let's start going through this now. The first, we've got all these shapes here. We've got a circle, we've got a square, we've got a rhombus, a trapezoid, and an octagon. We've got to calculate the area for all of them, so we're going to start with the circle here. The area of the circle is found using pi r squared. Our circle gives us diameter, so we're going to have to remember to divide our diameter in 2 in order to get our radius. And you can see us doing that right here. So I've got pi times 75 divided by 2, and I'm squaring the 75 divided by 2. So that works out to be pi times 37.5 squared, which means that pi is being multiplied by 1,406.25. which gives us approximately 4,417.86 millimeters squared, which is the area of our circle. So we're going to move on to the square now. And the square, of course, has the same length on all of its sides. Okay, so all 4 sides of a square are the same length. So when we're calculating the area of the square, it's just the side squared, which looks like this for our square. We had a side length of 69 millimeters, and so we're going to take 69 and square it to give us a total of 4,761 millimeters squared. And now we've got to calculate the area of the rhombus and later the trapezoid. So before we go any further with this, I've got another question for you guys. What are the correct area formulas for the rhombus and the trapezoid? If you got B, then you're correct. So let's take a look at how to get the area of the rhombus. We're going to use the formula we just saw in the previous slide. And so the area of the rhombus is the big diagonal times the little diagonal divided by 2. So we're going to pop in the information that is given to us in our rhombus over here. Our big diagonal is, of course, this longer one here. That's the 12 centimeter diagonal. And then our little diagonal is the 6 centimeter diagonal right here. 12 times 6 divided by 2 gives us 36 centimeters squared. So the area of the rhombus is 36 centimeters squared. And next we got to do the trapezoid. So we also know this formula from the previous question. So the area of the trapezoid is found by taking the big base, adding the little base, and then multiplying those by the height, the sum of those two by the height, and dividing that by 2. So if we plug in the values we know, we've got the big base here, which is 0.9 decimeters. It's the longer of the 2 bases that is our big base, so 0.9 decimeters. And then we're going to add 0.3 decimeter base here, okay? And we're going to multiply those two, the sum of those two, by 0.6 decimeters, which is our height. So according to the order of operations, we have to do what's in the brackets first. And so we're going to take 0.9 plus 0.3. That gives us our 1.2 here. And it's 1.2 that we've got to multiply by 0.6 and then divide by 2. That's going to give us 0.36 decimeters squared. So the area of the trapezoid is 0.36 decimeters squared. Now that just leaves us with our last cutout, which is the octagon. So to calculate the area of the octagon, we're going to use this formula here, which I say is the area of the octagon, which it is because our polygon is an octagon, but this formula actually goes for all regular polygons. So we're going to break down and just identify how these different parts, which are the side length, the apothem, and the number of sides, are going to apply to our particular octagon. So in this case, the side length, well, that's given to us in the problem. It is 30 millimeters. I'm going to write that up there. And then the number of sides, that's also given to us in the problem because, of course, we're dealing with an octagon. So I just count up the sides. Octagon has 8 sides. So n is going to be 8. And now the apothem. You might take a look at our figure and wonder, where am I going to get the apothem? Because it's not actually directly given to us. But remember, the apothem is actually measured from the center of a polygon, and then it intersects one of the sides perpendicularly. So if I start at the center and I intersect my side perpendicularly, it actually gives me the equivalent of half of the measure that I am provided with. So I've got this distance between two bases, or two sides, sorry, the two sides of my polygon, and that is 72.4 millimeters. And if I divide that measure by 2, I get my apothem, or the equivalent measure to my apothem, which is going to be 36.2 millimeters, just like that. So these are actually the 3 measures that I'm going to plug into here to calculate the area of my octagon. So 30 times 36.2 multiplied by 8 divided by 2 gives me 8,688 divided by 2, which ends up with an area of 4,344 millimeters squared for my regular octagon over here. So now we're going to calculate the area of the rectangle. And the rectangle I'm referring to is actually the entire lid with the cutout still there. Okay, so it's as if we haven't done anything to it yet. So we're going to take the base and multiply it by the height. And I've got the dimensions here. So 3 decimeters base times 3.2 decimeter height is going to give us an area of 9.6 decimeters squared. So the area of this whole board before the cutouts are taken out is 9.6 decimeters squared. So now we're just down in the final stretch of our problem here, where we've got to take a look at this area of the surface that we're actually going to varnish. So I'm calling that the area of the board. And to get that, we can apply 2 different strategies. We can either look at this as taking the area of the rectangle that we just calculated and then removing the sum of all the cutouts. So you see all the areas that we calculated added together, and we're removing that from the area of the rectangle. Or we can take a look at it. We can find the area of the board, which is, of course, the varnished surface, by taking the area of the rectangle before the cutouts and then just removing each of the areas individually. Okay? And actually, that's the one I'm going to opt for here. So you can see us taking away all the individual areas that we calculated previously. There is a problem, though, because none of these are really in the same units. I mean, millimeters squared, that's repeated 3 times, but everything else is sort of different units. So I've got to make sure that everything's in the same units before I calculate any further. And before we get to that, I actually have another question for you guys. When you have more than 1 unit of measure, which strategy should you choose? Convert the units of measure for length before calculating the area of different shapes? Or convert the units of measure for area after calculating the area of the different shapes? Actually, it doesn't really matter, okay? But you do have to make sure that you convert properly. And so I'm going to look at how to convert area because, of course, we chose the strategy where I did all my area calculations and I didn't convert before I started calculating. So I have to remember with area that with the measures of area, as I move from one unit to the next, I have to go by factors of 100 every time. This is different from when I'm dealing with lengths. With lengths, it's by a factor of 10 every time, but with area, it's a factor of 100 every time. And remember I said earlier that I was going to put everything into millimeters squared because already 3 of my cutouts or my areas are already in millimeters squared. So everything else, that just leaves 3 others that I got to move into millimeters squared. So here we go. When I do my conversions properly, given that I'm already in area, so I move with every step, I'm going to move by a factor of 100. So that means that I now have 96,000. And then I'm going to subtract what was already in millimeters squared. So that stays the same at 4,417.86 minus 4,761, which you'll notice also didn't have to be converted. And then I'm going to subtract 3,600 here, which is centimeters squared into millimeters squared. And then I'm going to subtract another 3,600, which is decimeters squared into millimeters squared. And then my final subtraction of 4,344, which was in millimeters squared so that got to stay the same. When I subtract all of those, it's going to give me 75,277.14 millimeters squared, which gives me approximately 752.77 centimeters squared, or again, approximately 7.53 decimeters squared. So the final answer to our problem here is the surface area to be varnished is approximately 7.53 decimeters squared. Okay, for our last example, we're going to take a look at the skating rink here. So here are the dimensions of your local ice rink. What is the total length of the boards that form the contour? And how long does it take the Zamboni, which resurfaces 25 meters squared of ice in 14 seconds to cover all of the ice? So we've got our ice rink broken down here into one big rectangle in the middle, 2 little squares, 1 on each side, and 4 quarter circles. And I've got a question for you before we go any further than this. True or false? Is it possible to break down the rink in another way? The answer is true. Let's take a look at that. So we got the same rink, except we divided a little differently. We've got these 3 rectangles, 2 shorter ones on either side, and 1 longer one right in the middle. There's no more of those little squares on the sides. And we still have our 4 quarter circles, which of course, when you push them all together, actually makes 1 complete circle. So we're going to go back to the original diagram here to do our calculations, right? And the first thing I want to do is look at the total length of the contour board. So it's what you see in red there. And that is going to be the perimeter of our ice rink. And it's calculated looking at the 4 circle quarters plus 2 times the length plus 2 times the width. So when I plug in the values, this is what I get. And I just want to take a moment to kind of explain that. Well, there's your circumference of the circle formula here, 2 pi r, that's the circumference of an entire circle. But of course, there's 4 quarters. So we're going to divide that entire circle by 4. And because there are 4 quarters, we then have to remultiply that by 4. So this is what we get here. And I just want to explain that essentially what's happened is we got to cancel out the 4s, right? So that leaves us with 2 times pi times 10, which is the radius of our circle. Now, if I take a look at what's going on with the 2 times the length, it says 2 times 40, and 2 times the width becomes 2 times 10. And some of you might be wondering where that came from. But if the radius of my quarter circles, or the entire circle, is 10, then that means that I actually get to remove 10 from either side, leaving me with this distance in between. And I don't want to cover up the 30 meters because we're going to go back to that later. But the distance in between here, that's going to be 10 meters. Okay, and then I'm going to do the same thing to the width, to the length down here. So I have 60 meters, but I have minus 10 meters on either side. So if I cut that here and here, the distance between those 2 lines, my little pink lines, is going to be 40 meters. Okay, so that's where that's coming from, because remember, I take care of the circles here, And so when I'm talking about the lengths and the widths, I'm really referring to the dimensions, the shorter part here, and then the two longer boards, the long sides of that rectangle, okay? So that's where those numbers are coming from. That gives us 20 times pi plus 80 plus 20 for a grand total of 162.83 meters. So that means the perimeter of my ice rink is 162.83 meters. All right, so I'm going to erase these two lines here because we don't need them anymore, but I'm going to leave those measures up there. And we got to get a plan going to talk about the surface that the Zamboni is going to cover and how long it's going to take for the Zamboni to do that. So first we've got to look at the area of the 4 quarter circles, also the area of the 2 squares, and the area of that rectangle in the middle. And then we'll take the time needed to resurface the rink into account. So this is what that looks like. And see, I told you I'd be using my numbers again, so that's why I left them up there. So to look at that, those first 3 points here, we're going to look at the area of the entire rink. And so the total area is found by taking the four times the area of the quarter square circles. Sorry. So we've got the area of the quarter circles here, multiply that by 4. And then we're going to take the area of the squares, which is here and here. And because there are 2 of the 2 squares, we're going to take the area of a square and multiply it by 2. And then we just have the 1 rectangle in the middle. So the area of the rectangle is only taken into account once. All right, this is what the formulas look like before we put the numbers in. So you see now we're dealing with the area of a full circle, which we then divide by 4 because we've cut it into 4 parts. And then we're going to multiply by 4 again because there are 4 parts. And then we've got 2 times the side squared, that's for our squares, plus base times height. All right, when we actually put in the numbers, again, our 4's canceled out. So we're really just left with the area of 1 full circle, pi times the radius squared, and the radius is 10. So pi times 10 squared plus 2 times 10 squared, and that is 10 squares. So 10 times 10, and there's 2 squares, plus 40 times 30. So remember, it's the area of that inner rectangle. And the inner rectangle has 40 length right there. But for this calculation, we actually have to use the whole distance between the 2 sides there. So that's why we're going back to using 30 there, right? Because we want to get that white rectangle in the middle. So this leaves us with 100 pi plus 2 times 100 plus 1,200, which gives us 314.16 plus 200 plus 1,200 for a total of approximately 1,714.616 meters squared. So 1,714.16 meters squared for the entire rink area. Now we need to look at the time that it's going to take to resurface this rink. So we already know that our Zamboni can cover 25 meters squared in 14 seconds. So we're going to set up a little proportion to allow us to figure out, well, what is that equivalent to if we've got 1,714.16 meters squared? How long is it going to take to cover that surface? If I manipulate my equation to isolate my unknown time here, I'm just going to use cross product, and that will give me 1,714.16 multiplied by 14 and divided by 25 for a total of approximately 959.93 seconds, which, of course, there's 60 seconds in every minute. So if I divide this number by 60, I get approximately 16 minutes. So that takes about 16 minutes to resurface this rink. Some of you might be curious about the actual size of a rink. So I've got this last little image here to show you, okay? So remember, there's our rink on top, and I'm going to take the measures out now so you can see that a little better. We got our rink on top, and this is an actual rink below here. So it's not that much different, but we just rounded out the numbers a bit to make them a little easier to work with. But a real rink is 60.96 meters by 30.48 meters. And that's it. We're done. So that brings us to the end of this video on finding perimeter and area in plane figures. It's actually one of 2 videos. So I'd encourage you to go check out our second video. And if you'd like to do any exercises to make sure that you understood the content all right, then you can check out the exercises below that are associated to this crash course. Until next time, I'll see you guys later.